Hey everybody, Mr. Smith here. Welcome back. In today's deck, what we're going to do is take a look at Coulomb's law problems, and we're going to move the needle forward, and we're going to take a look at ones that involve forces in combination. So they could be combinations that are linear, combinations that are along some kind of other geometry. But the big thing is we're going to have the unit vector skills behind us so we can treat these complicated problems like a lot of simple little ones and move forward with them. So let's go ahead and dive right in with this one. Here we've got a problem that is taken from the textbook. They say 3-point charges are placed in a row, and what we need to do is figure out the net force acting on the one in the middle. So what I want to do is just outline very quickly. We're going to use Coulomb's law. We're going to find the forces that act between the two sets of interactions that I see going on here, and we're also going to keep in mind that we're never going to get wrapped around the axle of a minus sign. That we're going to use our common sense when we assign directions to things. So the first thing I want to do is give you a notation that I use. I'm going to call this Q1. I'm going to call this Q2. And I'm going to call this Q3. And what I want to introduce you to is a symbol of notation that I use for these complicated problems that I really suggest that you think about using. What I'm looking for is the force that acts on charge 2 because of charge 1. So I'm going to call this the force of 1 on 2, or force 1, 2. And so the way I'm going to lay that out is this is just K times 3 microcoulombs. And we'll get right into the Coulomb's law math here, 5 microcoulombs. And then distance squared, 0.2 meters, whole thing squared. And we'll grab for our calculator in a second. But I want to stress the idea of the notation. So the other force that I'm looking for is what I call F32, the force of 3 acting on 2. So in my notation, that's going to look like this. So F32 is going to be almost the same exact thing as what we had a second ago, but let's go and get them. So we've got 8 microcoulombs, 5 microcoulombs, and then this distance is 30 centimeters, so 0.3 meters. And don't you dare forget to square it, okay? So what we're going to do is get those numbers. So we're going to pause right here, get those numbers, and then move forward. Okay, we're back. And so what we've done is calculate the force of 1 on 2 and the force of 3 on 2, and we've figured out what they are in newtons. The biggest thing you want to do is just use your common sense at this point. We're trying to imagine what is the direction of these forces, and here there's no substitute for common sense. So the vector direction that I want to give to this pair right here is to imagine that I'm standing on Q2 and ask myself, am I pulled to the left or pushed to the right? And so since I see opposite charges here, I realize that force of 1 on 2 goes to the left. And so what I do then is make that a negative 3.375 newtons in the I direction. So similarly, if I park myself again on charge 2 and imagine what is this guy doing, I'm going to see that I'm going to be tugged to the right by this force. So this is actually going to make force 32 positive 4 newtons in the I direction. And then the resultant force is just the sum of all those forces, and I'm going to get that is 0.625 newtons, and that's going to be, and I'll skip the end. Well, no, I have room. So 0.625 newtons in the I direction. Okay, so biggest thing, make sure you don't lose your head about the minus signs, and just use that common sense of imagine where you're standing, and that's what you want to visualize for the thing that's experiencing the force. Okay, so the one other example that we wanted to treat in this deck is considerably more difficult than that one, but there's a lot of symmetry to this one. And so in this topic, you're going to become a big fan of symmetry, because it makes the calculations repetitious. It makes them reusable. So you really only have to do them one time in some cases if there's a lot of symmetry. So really what this question is going to boil down to, once we get the Coulomb's law stuff out of the way, is it's going to become a geometry problem. And since we have unit vectors, it's not even going to be that bad of one. Okay, so here's the deal. We've got 3-point charges. Find the magnitude and direction of the force acting on each charge. Yikes. Okay, so here's Q1, here's Q2, and here's my Q3. So I hope it's clear that by the symmetry of all this, that we agree that the magnitude of the force on all of them is the same, that the force of 1 on 2 and 1 on 3 and 3 on 2, they're all going to be equal to the same number. So I've got K, I've got 5 microcoulombs, and we're going to square that. And then the side of the triangle is 0.2 meters, and we'll go ahead and plug that in. And I'm going to grab my calculator here and go do it. Okay, and so when we do that, we get 5.625 newtons. Okay, so that's the force that we're going to be using. What I want to do then is show you how we can break this down and you really use unit vectors to our advantage. Okay, so we've got our force of everything acting on everything else is 5 and 5/8 newtons. And here's what we're going to want to do. It's really important to be organized more than anything in this type of problem. So let's go look at one charge at a time. So let's look at the forces acting on Q1. So what I've got is, if I isolate on this guy, and what I'm going to do is drop a coordinate system right in the middle of Q1. And then it should be obvious that since all these charges are the same, I've got force of 2 on 1 acting in this direction right here. It should also be obvious that I've got force of 3 on 1 acting along this line right here. So I've got this guy going like so. And that those two forces are both equal to 5.625. So here's force of 3 on 1. What I want to do then is use symmetry wherever I possibly can and use it to my advantage. So it doesn't take a lot of insight to realize that as a vector picture, what I'm going to do if I think about breaking down force of 2 on 1 is that it's going to be partly up, so that would be a j component, and then partly across, that would be an I component. Same thing for force of 3 on 1, and the way it's going to break down because of symmetry will be the numbers are going to be exactly the same. And what I'm going to do when I can is I'm going to use the fact that if I see numbers canceling, I'm going to snag that. So I'm going to bet that these I components cancel. And so I'll prove it to you. Let's go ahead and get it. By geometry, the interior angle of this equilateral triangle is 60 degrees. We've bisected that. So each of these is a 30-degree angle. That's 30, and that's 30. And so what I've got here at the top of, if you want to get down and dirty, this is what you do. F21 of x is this component. And we'll break this one out here and call it F21 of y. And we'll get busy with the math. So F21 of x is going to be 5.625 times the sine of 30. And F21 of y is going to be 5.625 times the cos of 30. And we'll go and get those numbers right now. So this one right here is 2.813, and that will be in the positive I direction. This guy right here is going to be 4.87, and he is going to be in the positive j direction. So I'm allowed to use my common sense at this point. I know these are similar triangles. I can go through it and do the same exact math and show you that F31 x is going to be negative 2.813 in the I direction, and that F31 of y is going to be the exact same thing as F21 of y, so which is 4.87 j. And so long story short, the answer to what is the net force acting on Q1, this turns out to be a pretty simple one because the top guy gets canceling forces. And what I'll have is, if I get some of the forces, so the net force acting on both of them on Q1 is going to just be 4.87j plus 4.87j, which is going to be 9.74 newtons in the j direction. Okay, so those are all the forces on Q1. Let's go check out one of the other ones. So we'll go and attack Q2. So we've got Q1, Q2, and Q3 here. And let's go zero in on Q2. So here we've got a coordinate system, as we saw before, this is going to be force of 1 on 2 right here. And there's going to be the same kind of symmetry that we saw before upstairs. So what I'm going to do is extend my south line there, and I'm going to go hunting for, this is going to be F12y, and this guy over here is going to be F12x. But I can reuse those. So I did the math for those things already. So let me just come up here and write more neatly. Force of 1 on 2 in unit vector form looks like minus 4.87 in the j direction. And then plus, nope, that's going to be minus, what was the other component? 2.813, I think. 2.813 in the I direction. Okay, so I mixed up my i's and my j's, but that's no big deal. Okay, so that's force of 1 on 2. Now, force of 3 on 2 is going to be really handy. That's easy to do. So force of 3 on 2 is just straight across to the left. So that's equal to 5.625. And it's going to be in the I direction, except it's to the left, so it's in the minus I direction. And all I have to do to lump these together to get the total force on 2 is to add unit vectors. So adding unit vectors, I'm just going to take a second and add these things together, but I'm going to combine the i's with the i's, and there's nothing to combine with the j's, but I'll pause and I'll go ahead and get that. Okay, so what I get is negative 8.43 newtons in the I direction, and then my j was minus 4.87 in the j, and there you go. So very, very similar for Q3. I'm not going to treat that one, but go ahead. You're going to work this out for homework. So go ahead and get it. And as always, bring your questions to class. Take care, and thanks for watching. Bye-bye.